Okay. So how many people? 37. Yeah, not bad. Hello. Hi. So today, more divide and conquer, but not so insanely difficult. Not counting colorings anymore. Multiplying things, well, adding and multiplying. And so we're going to cover, well, 3 algorithms. So the first one is pretty easy. And it's not a divide and conquer algorithm. It's just to sort of get the ball rolling. So we're going to cover Euclid's algorithm, and Karatsuba's algorithm, and then Strassen's algorithm. And yeah, you'll see why I chose these 3, I hope. So Euclid's algorithm it's a nice starting point. Actually, a couple of years ago, I started the course with Euclid's algorithm because it's one of the earliest algorithms. So it was included, I don't know if it's known earlier, but at least it was known to Euclid because he included it in his elements around 300 BCE. And it's for finding the greatest common divisor of 2 numbers. So suppose we're given 2 numbers, which just, let's suppose that they're positive integers, right? So they're natural numbers, because probably Euclid was dealing with natural numbers. So we're given A and B, and we're asked for angle bracket AB, where angle bracket denotes greatest common divisor, okay? So this you need to find the greatest common divisor in all kinds of applications. So let's suppose you have A, you think of it as a pile of stuff, and you have B. This may be a little bit smaller. Let's make B like this. Do people know Euclid's algorithm? Maybe. Poll. I can set up a poll. Yes. Okay. Some people do. Yeah. Okay. Well, we'll go through it just in case. Back. How do I close the chat? Okay. Here. Yeah. Chat. Go away. Okay. I close it like this. So okay. Let's suppose that this is A, and this is B, and we want to figure out the greatest common divisor of A and B. And we look at it and we think, well, okay, so we take copies of B and we pile them on top of each other. Right? These don't look the same, but let's pretend they are. So if we think each of these is an integer number of, so this is some number times greatest common divisor of A and B. Why? Because the greatest common divisor of A and B is the divisor of B. So this copy of B is some, so I don't know, what are we going to call this? Let's say that this is C. No, let's not say that this is C. What are we going to, let's leave it as a question mark. Can people read this? Okay. Not well. Okay, maybe I should make it bigger. Okay, so it's question mark times greatest common divisor of A and B. Okay, and then we get same thing. The next copy of B is, okay, let's say that this is X. I want to say X times. I'm not going to write times as a cross because I wanted X. Okay. X times AB. And this is X times AB. Now we think, well, okay, A is some Y times AB, greatest common divisor of AB. right? So each of these is some integer number of integer multiple of the greatest common divisor of A and B. And this is an integer multiple of the greatest common divisor of A and B. So this gap here, that also has to be an integer multiple of A and B, right? Because if you think you take an integer number of copies of greatest common divisor of A and B and you subtract a bunch of integer multiples of the greatest common divisor of A and B, what you're left with is an integer multiple of the greatest common divisor of A and B, right? So, okay, Euclid's algorithm, the way Euclid proposed it was you take A and then you start. So let's suppose A is the larger number, and you start subtracting copies of B from it, right? Until you get a number which is smaller than B. Okay, if you get 0, if you subtract B from A multiple times and you end up with 0, then A was a multiple of B, and you're sort of done. You know the greatest common divisor is B. Okay, otherwise you subtract stuff away and you end up with something that's smaller than B. Okay, so that's this. So then you know that this is also an integer multiple of the greatest common divisor of A and B. So let's call this C. So then greatest common divisor of A and B equals greatest common divisor of B and C. Okay, now doing this subtraction a lot of times is kind of pointless. It's slow. So what we say is that greatest common divisor of A and B, well, what we say is that C equals A mod B, where we hope everybody knows what mod means, right? The first time I was at, well, the second time I was at TA, I was at Toronto, and the professor had told me I was supposed to teach the students why primality is in NP, which now we know it's in P, but even showing that it's in NP requires some fairly sneaky group theory. And I went in and wrote this, and they said, what's that? And I said, oh, GCD. And they said, what's GCD? And I said, have you done modular arithmetic? And they said, no. And I thought, oh, this is going to be a fun tutorial. Okay, have people seen mod? So in C, this is just, the operator is just a %. Yeah, good. So this is, remember you have mod and div. And mod is div is the number of times B goes into A, and mod is the remainder. Okay, so fortunately I will never actually show you the proof that, okay, so we'll go through the example. This in the notes, it's incorrect, but I just fixed it. I'll post it later. So this, let's assume this is one step. We're not going to do repeated subtractions anymore. We're just going to do a mod. So I'll move this chair out of the way. So for example, what is GCD of 168 and 78? Well, 168 mod 78, well, the largest multiple of 78 that's less than or equal to 168 is 156. So 168 minus 156 equals 12. Okay, so this is 12. Okay, so then we say, okay, well, what's the greatest common divisor of 78 and 12? And the 12 times 5 is 60, 12 times 6 is 72. So this is 78 mod 12 equals 6. And the greatest common divisor of 12 and 6 is, well, what's 12 mod 6? It's 0. So this, we say, okay, greatest common divisor is 6. Because, like I said, if you subtract copies of B away from A and you get to 0, then you know that B actually divided A. Okay. 15 minutes, 10 minutes already. I hope this is recording. Yes, it says it's recording. Okay, so now people sort of remember what mod is. So how long does this take, right? So let's think about it. So this was published about 300 years BCE. And so like 2,300 and something years ago. So, you know, I mean, people studied, is it correct? Yes, obviously it proves it correct. The proof of correctness is thousands of years old. Presumably Euclid actually proves it correct. But then, you know, you think, how long does it take? Well, if you do this subtraction thing, it's going to be really slow. Because if I give you, like, what's the greatest common divisor of 1,007 and 5, you're going to subtract 5 away from that. This is actually going to take, now I'm going to use a weird symbol. This can take omega A time if you do this repeated subtraction, where you've seen big O. I don't know if you've seen big omega. But big O, some people think of big O as meaning worst case and big omega as meaning best case. Never say that. You can use either of them for either worst case or best case. We'll get into this in another class. What this actually means is sort of, what big O means is sort of roughly at most about. Okay, it actually stands for on the order of, but it means at most about. Big omega means at least about. So actually, at least for sufficiently large values, at least a constant factor times this plus some constant. Okay, so we'll see the actual technical definition. But so think of this as at least about A. Right. So if I give you 1,007 and 5, it's going to take you, and 5 stays a constant. 5 is a constant. It's going to take you about 1/5 of A over 5 steps to figure out that the answer is 2. Not 2. The answer is 1. The difference of the mod is 2, but the GCD is 1. I have a paper due this evening, so I was up late for the past several nights. Actually, I was inspired to write the paper because we were talking about Euler tours, and it's something that I've been meaning for years to write about Euler tours. Okay, but how long does it take if you do this mod trick? Well, let's just count the number of steps. Let's pretend that we don't care how long mod is going to take us. How many steps are we going to do to find the GCD? So this actually wasn't analyzed until 1844. So you know the algorithm has been was around for 2,000 years, over 2,000 years, before anyone actually asked how long does this take. So that was sort of the beginning, according to Wikipedia, the beginning of complexity theory. So the beginning of people asking, is this hard or is this easy? So it's pretty easy. So this says if you do the repeated multiplication, if you do the repeated subtraction, it can take you linear time. Are people saying things still in the chat? Oh, would it be correct to say that if the subtraction is 0, then AB equals B, else C equals A mod B? Yes. Okay, okay, we covered this. Yes, it's logarithmic time. Why? Well, now I have to remember, where is my eraser going? Here. Okay. So let's suppose that B is so if B is, I can't remember if this is greater than or equal to, but let's say if B is less than A over 2, then yeah, okay. Then if B, then A mod B has to be less than B is less than A over 2. Okay. But if B is, let's say this is less than or equal, A mod B is less than or B, which is less than or equal to A over 2. So, okay, A mod B is less than A over 2. Okay. Right. So if B is strictly greater than A over 2, then A mod B is less than A minus B, right? Or less than or equal. Yeah, less than or equal. Well, actually, I guess it's equal. Which is less than A over 2. Like I said, it was, I'm running short on sleep. Okay. So in both cases, when you say, okay, we go from asking about A angle brackets AB to asking about angle brackets BC, where C is A mod B. So C is less than half of A. Okay. So since we assumed that A was the larger number, then the sum of these two numbers is shrinking by at least a quarter, right? So if you're shrinking something by a quarter, then essentially, how many times can you do this before you get down to constants? Well, log base. Now I'm not sure. Log base 4/3 of A plus B. So let's just put an O in front of it. Okay, so actually this is, if you've got the O in front of it, it's just log A because A plus B is then almost twice A. Okay. I'm not sure if in the notes I wrote 3 over 4 instead of 4 over 3, but it's 4 over 3. Okay, so logarithmic time. So that was easy. Kind of surprising that it took like 2,000 years to get to somebody actually asking how long this took. But actually, this Gabriel Lamé showed that actually the worst case is when the A and B are consecutive Fibonacci numbers. And in that case, it uses 5 times the number of decimal digits in A, I think. So he got actually quite a precise bound because back then people hadn't invented big O. So you had to actually do the exact analysis. So let's just stop and think about it. So when we say, how long does this take? Well, it would seem to take, so are people asking, because the chat is getting stuff. Oh, rats. Okay, so I should leave this. Okay. Now I have to, was anybody asking? Is it in log time? Okay, so somebody asked, is it in log time? I have the chat window over. So yes, it's logarithmic in the sum of the numbers. But now, Lamé said, okay, it's linear in the number of digits. Now, this gets to a question which usually I deal with later in the course. Usually, I've taught this course twice in English. I taught it in Spanish, but I wasn't allowed to do mean things when I was in Chile. I wasn't allowed to make people account for colorings or anything like that. So really this course, this nice challenging course, this is my third time teaching it. Okay, so I TA'd it at Toronto and Queens, and yeah, that's about it. And I taught, no, I never taught algorithm, just algorithms. Okay, so when I tell you about the size of an input, okay, I'm just going to scroll down so I have the most recent check. When I talk about this, when we talk about, you know, how big is the, how do we measure how long something takes? So if somebody gives us these two numbers, A and B, and we talk about how big they are and how long Euclid's algorithm takes in terms of the size of the input, well, it's kind of natural to say the size of A and B are respectively A and B, right? These are numbers, they're that big, that's sort of what it means. But usually the default is actually to talk about sort of the size of the piece of paper you would need to write these things down. Okay, so if I'm going to write you an instance of a problem, the size of the instance is the size of the piece of paper. Now I could write very small, but let's suppose that I'm going to write in like a fixed point font. How much paper do I need? Now I can use like some really weird encoding of the numbers or something, but let's just assume that these are numbers in decimal, like Lamé was talking about. And so, okay, A and B, and how big, if we measure A and B as the number of decimal digits in them, then this is linear, right? Lamé showed that in the worst case, this is linear in the number of digits. Now, that is going to come up later in the course when we talk about algorithms like knapsack. So not algorithms, problems like knapsack. Because knapsack, now I just have to make sure that my alarm is going to go, because I put it to do not disturb. We have 1 minute and 44 seconds before the alarm should go. Let's see if it goes. Because I don't want to be disturbed by people emailing me or something, but I do want to be disturbed by the alarm telling me to restart the camera. Okay, so knapsack, later in the course, I'm going to give you a dynamic program that will solve instances of knapsack with a knapsack of size n, and it'll solve it in something like n time, at least polynomial in n. But then I'm going to tell you that knapsack is a boom problem. It's an NP-hard problem. And people are going to think, like, why? Okay, so because n, if something runs in time n, then that's linear in n, but it's exponential in the number of digits you need to represent n, which is you only need log n decimal digits or log n binary digits, and it doesn't really matter what the base of the logarithm is, because that's just the base of the number system you're using, as long as you don't write in unary. In unary, you represent n as n copies of 1, and that takes space linear in n, right? So the number of the size of the instance, if you want to write n this silly way, writing with n ones, then yes, okay, then it's linear in the size of the space you use then. How are you going to remember this? It sounds like some weird, subtle, mathy thing. But this is actually, you can remember this by watching a movie. So This is not going to be one of those courses where I get to kill time by playing movies in class. I'm not going to play the movie. I'm only going to talk about the movie. Has anyone heard? Has anyone heard that factoring is supposed to be hard? Now, frequently, even Bill Gates, I think, messed this up one time when he talked about factoring prime numbers. So what people mean is factoring numbers into primes, into their prime divisors. Okay, but yes, so it's the base of some crypto. Okay, it's also, it's believed to be hard unless you have a quantum computer. So one of the things that got people interested in quantum computing was Shor's algorithm, where Shor showed that you actually can factor quickly on a quantum computer. We don't know quite if we can build those and actually run Shor's algorithm on them yet. Okay, so factoring, yes, is the basis of a lot of cryptography, public key crypto systems, RSA, stuff like this, which you may have studied, or you will study, or you might have heard of, or something. Okay, so it's believed to be hard. It's hard enough that people will like protect your bank account using crypto based on this problem, on the assumption that people can't, given a large number, people can't find it. So you take two large primes, multiplying them is easy, but then given their product, finding those primes from the product is believed to be difficult. At least we don't have a polynomial time algorithm for it. But let's suppose that I give you, I have to start this again. Yes, okay, let's suppose, I only have like 15 minutes. Faster, we must go faster, because I haven't got to Karasuba's algorithm yet. Okay, so let's suppose that I say, what are the factors of n? Okay, so what you can do is just write for I equals 1 to n, if n mod I equals 0, print I, and if n4. How many steps does this take? Like n, right? So this is going to print, it's not just going to print the prime factor, it's going to print all the factors. So factoring takes linear time. That doesn't sound super secure or hard. But it takes time linear in n. Okay? So linear in n is definitely polynomial in n. But it's linear in n is exponential in the number of bits you need to represent n. Okay, so that's why it's hard, because when we're talking about problems, we're talking about how big a piece of paper we need to write the problem down. Okay, so just think of factoring. If you want to find out more about factoring, there's this cool movie, Sneakers, from like the early 90s, actually. It's got lots of great people in it. And actually, I found out just preparing the lecture notes that Len Edelman, who's the A in RSA, which is the public key crypto system, actually, he knew the director, and he wrote the slides for when the mathematician in the movie presents how to factor. So, yay. So presumably those slides are correct. Okay, so what's next? Factoring, knapsack, RAM model. Oh yeah, we have to talk a little bit about running out of time. Let's talk about the model of computation. So if you do more algorithms courses, I believe there's actually is only really one more. Like there's Norberts, and maybe there's computational geometry or something which could use this. Frequently, we talk about something called the RAM model. Okay, well, we'll also talk about this Turing machine. Nobody really analyzes algorithms these days in terms of Turing machines, unless you're talking about like polynomial time or something like that. Because if you care about logarithmic factors, then you work on the RAM model, which is a more faithful representation of actual computers these days. So what is the RAM model? Well, so for us, if I talk about addition or something, usually I'm talking about numbers that fit in a machine word, and adding two machine words, you have this what's called bit level parallelism, which means you don't have to do this like digit bit by bit. You actually have a table in your computer and it just adds, right? So you can do addition of two numbers that fit in machine words in constant time. Multiplying is a bit tricky because multiplying is not in a complexity class called AC0. But actually, yeah, you can sort of assume that you can multiply. As long as the stuff fits in a machine word, you're good. Generally, as long as as long as the operation isn't too weird. For example, you can't say, oh, well, when this number fits in machine word, I can factor it in constant time. No, not that. But addition, multiplication, like I said, it's not AC0. So you don't really need to know, but but then these machine, so on a modern computer machine, your machine words are probably 64 bits. Like unless you have a really old machine. So these days, like everything, you can still get versions of software written for 32-bit machines, but I don't know if anybody still uses those. You generally have 32 bits or 64 bits. So the key thing is people talk about, we've got a word RAM. And then let's say theta. So theta, remember, big O is at most about, big omega is at least about, and let's say theta just means about. Okay. Log n bit words, where n is the size of your problem. Okay, so this is the general model when you design algorithms. Now, what this means is if your input is huge, you get bigger words. Okay, why log n? Well, because if your algorithm runs in polynomial time, you're going to use at most polynomial space, and you can represent a number that's polynomial in n in some constant times log n bits. So this means you can store pointers. You can actually you can jump around in the space that you've been using. You can jump around in your input, and you can jump around in the space that you've been using for your computation. Okay, Karatsuba's algorithm, Strassen's algorithm. Okay, so that's the RAM model. So as long as you're working with numbers that fit in machine words, then you can assume addition is constant time, and in this class, let's assume that multiplication is also going to be constant time. So what this means, and mod, let's say mod is constant time. Now, actually, there are weird things like parity. You can't count the ones in a machine word in AC0. Whatever, it's in the lecture notes, but we're not going to care about that. So for not too large numbers, you can assume that arithmetic operations are constant time, and like usually you don't run into huge numbers unless you've got some psycho who makes you do something like count 4 colorings, which is like exponentially huge, and then you can get these really big numbers. But I think even for the 4 colorings of that map, it fits in a long, so it should fit in 64 bits. Okay, so yeah, we've talked about the RAM model, the input size. So let's just okay, now we have to talk about the complexity of addition. Well, let's look at these two numbers. 8, 6, 4, 1, 9, 6, 2, 1, 7, 5, 3, 3, 9, 4, 0, 5. I told you that these will probably fit in a machine word on your machine, so you can, on your machine, your computer can add these in constant time. But how long does it take for a human being to do this? Okay, and this is important for Euclid's algorithm because remember I was talking about how many steps things took. But in order to talk about how much time it takes, we need to talk, if you're not assuming that your arithmetic operations, if mod doesn't take constant time, then you need to talk about how much time you need for arithmetic operations. Okay, so what's the standard algorithm for doing this? You go, okay, 6, 2, carry a 1, 9, carry the 1, 5, 7, 1, carry the 1, 15, 16. Okay. Now, how big can the carry be? Well, you can show by induction it's never more than 1 if you're just adding two numbers. Okay. Because when you start, the carry is 0, and assuming that the carry is at most 1, this is 9, this is at most 9, this is at most 9, plus a 1 is only going to be 19, so the carry is going to be 1 again. Okay. So this looks, as long as I can add single digits in constant time, which I can do this in time proportional to the number of digits. So linear time in the size of the instance in the amount of paper that you give me. If you give me these two numbers, I can write this out in linear time in the length of these two numbers. Okay, so addition is easy. Okay, now let's talk about multiplication very quickly. Not super quickly, but so how would I multiply? Well, how was I taught to multiply in primary school? 5 times 1 is 5, 5 times 2 is 0, carry is 10, carry the 1, 5 times 6 is 30, so add 1 gives me 31, carry the 3, 5 times 9 is 45, I get an 8. 5 times 1, 9, blah, 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 blah. And then I drop down, okay, so this is all zeros. And then I have a 0 and a 0, and 4 times 1 is 4. And I do this for all of these numbers, and I did this in the lecture notes. So how many digits are in this big pile of stuff before I start adding up the columns? How long is this going to take me in terms of the number of digits in my input? Do I still have, are people still here? Yes, well, some people. N squared, yes. If n is the number of digits, this is going to take n squared time. It's also going to take me n squared space, which is annoying, right? So I'm not just going to, it's not just going to be slow. I'm going to need a really big piece of paper. So you give me this on a little piece of paper, and then I need a big piece of paper for this. So there's a trick in the lecture notes, which I'm not really going to go through. But for example, okay, you can do this in linear space. For example, I can work out what this sum is. This is a 5, right? And then and then I'm done with this column. I don't need that anymore. Now I can work out what this column is, right? So I don't have this column anymore. So now what's this column? This is 5 times, so here the carry is a 1. And so I'm carrying this 1 over here. But the 5 is 5 times 2. This is a 0. 0 times 1, this is a 0. And then everything else is 0. So this is a 0. I think. And then, okay, so now I had this 1 in the carry. So this is, I'm done with this. So I'm just writing this out. This takes linear space. Okay. I can do this. Okay, so 5 times 6 is 30 plus 1. So this is a 1, and I've got this 3 carried over. Now, 0 times 0 times 2 is a 0. And 4 times, wait, it's 5 times 6. 4 times 1 is a 4. So this is a 5. Does that? That doesn't look right. 5 times 1, 5 times 2. Is that 505? Is in the course notes? Is this actually 505? Yes. Okay. This is going well. Yeah. Okay. That's correct. Okay. So you can see that as long as I keep track of these pointers, how many pointers do I need? Well, at most 1 for each digit down here. And I can calculate these, I can fill in these columns and sum them up column by column instead of calculating them row by row and then summing them all. So I can reduce it to linear space. So now we've got multiplication O(n) squared time and O(n) space. Okay? So now that's you know, okay, we're getting somewhere. We've got an improvement on what we were taught in primary school. But for a long time, you know, there are lots of different techniques for multiplying numbers. You know, you've got this, you've got these things where you count like different fingers and stuff like that. But actually, they're all going to be quadratic time. I mean, so we've been multiplying. Human beings have been multiplying things for thousands, probably just thousands, tens of thousands, maybe years. And we never, no, big O, remember, it's not for best case, worst case, it's not for time, it's not for space. It just means at most about. So in another class, I'm going to show you there's this, has anybody seen Stirling's formula for sort of, it's an approximation of factorials. Okay, it's got an O in there, right? And that doesn't mean good or bad. It doesn't mean time. It doesn't mean it's just a number. It means that this n factorial is like this, and then there's some difference which is like on the order of like n or log, something like that. I'd have to look up the Stirling formula again. Okay, so it hasn't got any semantics on it, apart from, like I said, at most about, at least about, and then we'll go into exactly what it means in another class. But now we have to get through Karatsuba and then Strassen. Okay, so there's this cool story that, so for thousands of years, we were multiplying things in quadratic time. And it seems like this is about the best we were gonna ever do. To the extent that this famous mathematician, Andrei Kolmogorov, Andrei, Alexei, I looked this up. It's correct in the course notes, in the lecture notes. Okay, so in a seminar in 1960, he conjectured that this is the best you can do. Okay, so notice that now I told you that computers can do this in constant time, but that's only for numbers that fit in machine words. So if the number is big enough, even the computer is going to need, if it does it does some standard algorithm. Before 1960, even the computers needed, for very large numbers, they needed quadratic time to multiply, quadratic in the number of digits. Okay, so there was this student in the course, 23 years old, Anatoly Karatsuba, in the seminar, and he went away, and a couple of days later, he came back and he said, no, actually, we can do it faster. And he showed Kolmogorov this divide and conquer algorithm that I'm about to show you now, which is kind of cool. Because the story goes that Kolmogorov was super impressed by this. Incidentally, if somebody does something like this to me, I promise I'll be super impressed too. To the extent that Kolmogorov wrote up the result with another algorithm about multiplication by somebody else, and put these two people's names on it, not his own, and sent it to a journal. And so Karatsuba found out about this when he got the preprints or the reprints from the publisher, saying, congratulations, here's this very nice paper of yours that he didn't know had been submitted. And if you do something like that, I promise I will also write up your result and send it somewhere. I just if you could write on it, this was done in 3110, taught by Travis. But yeah, that would be super impressed. Don't worry, I didn't. It's like okay, yeah. Actually, I don't promise. I'm not as enthusiastic as Kolmogorov. It depends what you prove, but okay. So, what was Karatsuba's algorithm? So it's divide and conquer. So I have half an hour. Okay. So let's take this example. So I'm just going to have time to do the example. Okay. So this is obviously. We can think of this as 8641 times 10 to the 4 plus 9621 and 7533 times 10 to the 4 plus 9405. Later in the course, I'm going to tell you about this Huffman's algorithm, which is this famous algorithm that he came up with to get out of the final exam in a course. I have to, like, my courses, they're not up to this level. Okay. So let's say, so we can split it up this way. So obviously, this multiplication is going to be 8, 6. Okay. Let's say that x1 equals 8641. x0 equals 9621. I have to remember how this goes. 7533. y0 equals 9401. Okay, so I don't have to keep writing this stuff out. Okay, so this product is x1 times 10 to the 4 plus x0 times y1 times 10 to the 4 plus y0. Now, the 10 to the 4 is just, the 10 is the base, and the 4 is n over 2. Right? If the length of these numbers is n, then they're nice. They're powers of 2. N is a power of 2. This is easiest, but you can do it in all cases. So you could figure out this works in general. Okay. So this is x1 times y1 times 10 to the 8 plus x1 y0 plus y1 x0 times 10 to the 4 plus x0 y0, right? So this you're just expanding this out, like first times this, this times this, this times this. Okay, everybody could do this. So how many multiplications is this? So instead of multiplying two n-digit numbers, I'm multiplying, well, I'm doing how many multiplications then over two-digit numbers? 1, 2, 3, 4, right? Now that doesn't seem to have helped me. And I'm also doing a bunch of additions. Because 4 times n over 2 squared equals n squared, right? So this is the complexity of multiplying, roughly the complexity of multiplying 2n over two-digit numbers, and I'm still getting the same complexity just for doing these multiplications. Okay, so we haven't gone anywhere. We're running out of time. So what Karasuba, his trick was to come up with these intermediate numbers, where he said Z2 equals X1, Y1. Z0 equals X0, Y0. Z1 equals X1, Y0 plus Y1, X0. Okay, so that means that this is just Z1 times 10 to the 8 plus, Z2 plus Z1 times 10 to the 4 plus Z0. So far, nothing impressive. Okay, what was the trick? Well, he said, okay, but look, this still takes 1, 2, 3, 4 multiplications. But what happens if we notice that Z1 equals X1 plus restart the camera. That means we're in the last 25 minutes. Z1 equals X1 plus Y1 plus Y0 minus Z2 minus Z0. Now, if we have, we still have time to just multiply this out. So let's just make sure that this is correct. It's X1, Y1 plus X1, Y0 plus X0, Y1 plus X0, Y0 minus, remember, Z2 is X1, Y1 minus Z0, which is X0, Y0. So you take the X1, so this cancels, and X0, Y0, this cancels. So you get X1, Y0 plus X0, Y1, which is exactly what you want for Z1. So this is true. This is a correct observation. And notice that he's getting this with only one multiplication instead of two. Okay, so that means if he computes Z2 and then with one multiplication and Z0 with one multiplication, and then computes Z1 with one multiplication and then two subtractions and two additions. But additions and subtractions are easy. Those are linear time. Then he's using only 3 multiplications of roughly n over two-digit numbers. Now, actually, okay, when you do these additions, then it can be like n over 2 plus 1. But okay. So is this fast? So in the in the lecture notes, I've actually done that for these things. I've actually worked out Z2 and Z0, and then I worked out this, and then plugged it all in, and it works. Okay, you do actually get this the product of these two numbers. I'm going to skip it because it takes a while. Does anybody really need to see that? No. Good. So how long does this take? Well, okay, so we saved one multiplication, but that doesn't really help us if it's just that multiplication, right? Because then, you know, we've saved like this, but we've got 3 times, instead of 4 times n over 2, we've got 3 times n over 2 squared. Well, that's only a constant factor. So we're saving like a quarter of the time. That's not going to help us. Of course, the trick is to use this recursively. So if you use this to compute, to figure out your the product of your 2 n-digit numbers, by working out products of n over 2-digit numbers, and you work out those 2 n-digit, 3 multiplications n over 2-digit numbers, and you work out those 3 multiplications of n over 2-digit numbers by each of those by 3 multiplications of n over 4-digit numbers. Okay, so how long does this take you if you do this recursively? Well, you get this recurrence, which is Tn equals 3 times the time it takes you to multiply n over 2-digit numbers, plus then something which is linear in n for the additions and subtractions. Yes, recursion, yay. Yes. So I think in the course notes, I think I said C was equal to 5. We don't really care what C is. We also don't care about this example, which is in the lecture notes. 20 minutes. Okay, so if you get this recurrence, okay, so have you seen recurrences in discrete or something? Discrete 2? Yes, good. No, no. Oh. Okay, I think the discrete 2 is not mandatory. Yes, no. Okay, about half the people. Okay, if you have this recurrence that says this function t is the time it takes you, is some function of n, and it tells you how long it takes you. Oh, right, we didn't talk about worst case. Where is worst case? Worst case used to be up there. Right, usually if we're talking about complexity, yeah, I should mention this. Usually when we're talking about complexity, I mentioned best case. People don't usually care about best case. Usually what we mean is if we say the complexity of this is n squared, it means that for sufficiently large inputs, right, where n is the size of the paper you're giving me, or n is the size of the input, however you're measuring it. N could be the number of vertices in the graph, something like that, right? N is this thing that you want to measure in terms of, and you say this takes n squared time. It means that as n goes to infinity, for some constant times n squared plus some, so for sufficiently large n, it takes me about n squared time to solve any instance of size n. Right? So this is worst case. Now, you can also talk about average case. It'd be like, okay, over all the instances, as if for sufficiently large n, over all the instances, on average, it takes me n squared time. Okay, if you choose one, well, yeah. And you can talk about the expected case complexity. Yeah, okay. So usually we talk about worst case. It is usually talk generator functions. Ah, yeah. Oh, yeah, I remember generator functions. Don't worry, we're not going to do generator functions in this class. We're going to have to do recurrences because Dal makes me. Okay, so let's get going. So this is some function. So we're going to say, let's say that t of 1 equals 1. Right? So we need some base case. So there are lots of books about generator functions and recurrences, and And we have enough to cover in this course without going too deep into this. Okay, so how are we gonna figure this out? Well, what you're gonna do is you're gonna say t of n, take this, just assume that t of 1 equals 1. But I want it to be written up here. So this equals 3. Well, we can plug this in and say, okay, well, what's t of n over 2? That's 3tn over 4 plus cn over 2 plus cn. Well, what's that? Well, that's just, what is tn over 4? Well, that's tn over 8 plus cn over 4 plus cn over 2 plus cn. Okay. So if we say, okay, we expanded out I times, what are we going to get? We're going to get 3 to the I times t of n over 2 to the I, and then plus sum of j equals 0 to I minus 1. Well, we're going to get, okay, cn, sum j equals 0 to I minus 1, I think, of, now remember, this isn't being multiplied by, sorry, this isn't being multiplied by any 3's. This is being multiplied by this 3. This is being multiplied by this 3 and this 3. Okay, so it's actually going to be 3 over 2 to the j. Okay, so and then you play around with this and you think, okay, so you plug in I equals log n, right? So let's plug in I equals log n. So can you still see this down here? For I equals log n, this is going to be, I need the space. For I equals log n, this is 3 to the log n, t n over 2 to the log n, plus cn sum j equals 0 to log n minus 1 of 3 over 2j. 3 to the log n, this is 2 to the log n is n, so this is t of 1, this is 1, so this is just 3 to the log n. And then this thing is, I worked this out last time. This is at most log n times, yeah, okay. So you have cn. So let's just, this sum is bounded by log n times 3 to the log n over 2 to the log n. Oop. Just a second. It's hard to do this. Yeah. Oh, okay. I worked this out and then I just skipped over it. Okay, so this works out to be order 3 to the log n 2. Okay. So this is all just order 3 to the log n. Don't, like, if I have more time, I can do this. So what is this? Well, 3 to the log n equals 2 to the log 3. LG means log base 2, okay? It's very frequent in computer science. We need log base 2 all the time. times log n, and then we can just swap these around. So this equals, I'm just showing, this is easy, but it's just a neat trick, and people got stuck on it in a previous year. Log n log 3 equals n to the log 3. So this is order n to the 1.58 something, something, something. Okay, so it's better than n squared. 15 minutes to teach Strassen's algorithm. That's insane. Okay, so Karatsuba's algorithm, you can do it in n to the, he showed that you can do this multiplication about n to the 1.58, n to the log 3. Okay, so this is, right, so after thousands of years, in 1962, somebody figured out how to do a multiplication in subquadratic time. Now, shortly after, people improved this. And actually, this is cool for people in Canada, because this was studied. There was an algorithm called Tomb, where instead of chopping stuff in 2, you chop it in k pieces, and then do sneaky multiplications of n over k things, n over k digit numbers. And that was done by Tomb in '63, and that was reanalyzed by Cook in his PhD thesis at Harvard on the complexity of multiplication in 1966. Cook is Stephen Cook. He was my logic professor at University of Toronto. He'll come up again in the course because he's the P versus NP guy. Yeah, so it's cool so the other thing, there's probably a bunch of stuff, it's in the course notes. But another cool thing is that people actually figured out how to get this down to n log n. And they did that in March 2019. So about 6 months before the first time I taught this course. And now it was then multiplication became n log n time. Okay, so that's cool. So addition is linear, multiplication is not worse than n log n. Okay, so now we can we've done addition and arithmetic operations on numbers. So what else can we work with? Well, how about matrices? So number integers are a ring, matrices are also a ring. We don't have time to talk about rings. You may have seen rings, fields, stuff. Okay, so you have addition and multiplication. So how long does it take you to add? Let's suppose that you can do addition of the components. How long does it take you to add an n by n matrix and an n by n matrix, assuming that you can add the entries in constant time? Well, right, you just add corresponding entries, right? So if you have A plus B equals C, then Cij equals Aij plus Bij. How many things do you have to do this for? Well, n squared, right? So matrix addition is O(n) squared time, assuming the elements can be added in constant time. Okay, what about matrix multiplication? So this gets a bit scary, because if you think about the algorithm we learned in high school, where it's A11, A12, A21, A22 times B11, B12, B21, B22, C11, C12, C21, C22. Okay, so to get an entry, Cij this is the dot product of the ith row of A and the jth row of jth column of B. So each of these are n entry vectors. So to do the dot product, okay, it's actually the transpose of the jth column of B. To do the dot product, you're going to multiply the first component by the first component, the second component by the second component, and then you're going to add all of these products up. That's going to take you n time, right? So to compute each entry of C, it's n time using the standard algorithm. And there are n squared entries of C if it's an n by n matrix. Right? So this is cubic. Now in numerical algorithms, you can, you have a matrix and it's like 1,000 by 1,000. Well, cubic in 1,000 is 1 billion. That's pretty nasty, right? Doing a billion, and then sometimes, so if you're training neural networks or something like that, you can have to evaluate the product of polynomials if you're doing PageRank, something like that. Multiplying matrices is not easy, right? So let's see if we can do it in something so the standard algorithm is cubic time. Standard algorithm is cubic time. So we'd like something better than subcubic for matrix multiplication. Now we actually don't know how fast you can multiply matrices. And it's an important question because multiplying matrices isn't just an important thing by itself, but it's used as a subroutine in a lot of other algorithms, including some algorithms we're going to see towards the end of the course for like counting paths and shortest path computation. And I have 8 minutes. So Strasse. So remember, this was after Karatsuba showed that you could do this sneaky divide and conquer to multiply integers faster. So Strassen did sort of the same thing, but for matrices. Now, I wrote out in the course notes. Okay, so here you have the standard. So what you would normally write is, like I wrote, Cij. So here C11 equals A11 times B11 plus A12 times B21. C12 is A11 times B12 plus A12 times B22, right? Right? You do, to get C11, you do this times this and this times this. To get C12, you do this times this and this times this. Okay, so if you actually write this out, C22 equals A12 B21 times B12 plus A22 times B22. Right, so how many multiplications are we doing here? So each of these we can think of, if we have n by n matrices, where n is some nice power of 2, for example, to keep things simple, and we've chopped it up into 4 submatrices, each matrix into 4 submatrices. So this requires 4 submatrices of size n over 2 by n over 2. So how many how many multiplications of n over 2 by n over 2 matrices do we use? Well, if we just do this, we use 8, right? 2 for each submatrix in C. Are people still here? Yes, generally. Okay. So if you do it the normal way, you use 8. Now that's 8 times n over, this is the same as with caret super, times n over 2 cubed equals n cubed. We're not saving anything. But now Strassen realized, so he came up with 7, I believe 7. So he did the same thing for matrices, 7, which I am not going to write out because that would take more than 5 minutes, but it's in the course notes. I also got it off Wikipedia. Because, hello. Okay, so as you saw, I've more or less memorized, like, I forget it, but every year you can memorize caret suba's the definition of Z1, Z2, and Z0, Z1, and Z2. The only tricky one is Z1, and like it's just X1 plus X0 times Y1 plus Y0 minus Z2 minus Z0, right? That's easy. Nobody is going to, and certainly not me, I have never memorized the Strassen's 7 intermediate matrices. So these are M1 through M7, and they're like the caret super Zs or Zs, whatever, but not easy to remember, okay? So what he does is for each of these intermediate matrices, you do some additions and subtractions and 1 multiplication, okay? So remember, additions and subtractions, they're in square time, so they're easy. And then you've got 7 multiplications. So Strassen showed how to use 7 multiplications of n over 2 by n over 2 matrices, submatrices. Okay, so again, if we just do that once, it doesn't save us. Well, what's the recurrence? Tn equals 7 Tn over 2 plus Cn. We expand this out. I sent this to my mother for proofreading, and she tells me I'm not allowed to say expand out because it's redundant. Expand is always out. So that's why it just says expand in the course notes. Okay. So this is, I'm just gonna, if this is not recording, I'm gonna cry. Oh, it is recording. Okay, this, what you get is n to the log base log 7, order n to the log 7. Log 7. And log 8 is 3. Log 7 is slightly less than 3. I think it's 2.807 or something. Okay. So n to the 2.807 maybe. Okay. So woo! Matrix multiplication in subcubic time. Now this there was that, and then there were a chain of things where people were like pulling this exponent down. For a while, people thought it was going to be 2.5, but then it was pulled under 2.5. Then for a long time, the best was this algorithm by, I think, by two guys called Coppersmith and Winograd. And then a few, like 5 years ago, Andrew Strother, in his PhD thesis, he managed to get it slightly better. And then Vasilevsky-Williams got it slightly better. And then Legal got it slightly better. And now it's something like 2.37. And now every time it changes by this tiny little amount, the whole theory community goes nuts. And it's changing by things like 1 in 1,000. There was also a nice result recently. I'm over time. There was a nice result recently. People at MIT, somebody in Vampala, showed that actually you can do Gaussian elimination, in slightly better than matrix multiplication time as it stands now. So they managed to find this way to get around matrix multiplication for something people thought you needed matrix multiplication for. So this is like theoretical computer science. It's like the gravitational constant. Like, do normal people really care what it is in its 5th decimal place? No, but physicists get excited about that. So yeah. I don't get super excited when this number changes, but some people do. So that was Strassen. In the next class, we're going to be doing the fast Fourier transform, which is showing we saw integers are a ring that has addition and multiplication. Matrices are a ring that have addition and multiplication. Another ring is polynomials. Okay. So how fast can well, you can add polynomials pretty easily, right? They just add the corresponding coefficients, but how fast can you multiply polynomials? And so to do that quickly, you use something called the fast Fourier transform. I'm not going to be teaching that though, because a friend who's a postdoc, he needs teaching experience, and also I never actually learned the fast Fourier transform when I was an undergrad. Because it's not something, somebody said they learned it at that in Dirk Arnold's course, but usually it's not taught to CS people. But this guy, he's an electrical engineer, so he wants teaching experience, and so he's going to teach you the fast Fourier transform, basing it off lectures by Eric Demain, who actually is a Dal grad and is now a prof at MIT. And if you want, you can watch his to get prepared for Max's lecture. You can watch the lecture by Demain. Don't know if I'm spoiling the surprise. Don't watch the lecture by Demain. Just wait for the lecture by Max. Questions, comments? That got a bit fast towards the end, I think. But stuff is in the lecture notes. Otherwise, people can go. I mean, we're 3 minutes over time. Shoo, lunch. Will the lecture notes be updated? Yes, I fixed that little bug right at the beginning. I posted them, then I updated them when my mom fixed some of my English mistakes, and now I'll update them again. But yeah, the lecture is currently in, like, I have a few paragraphs of chapter 4, but Demain has course notes on the fast Fourier transform. Like I said, I have this paper deadline today, so I may not get the course notes written for Wednesday before Wednesday. But Demain has nice course notes on the fast Fourier transform. Thanks. It's the conference is going to be at Dal. It's run by Meng. So I've been meaning to write this up for ages. It's just Euler tours, and then I was like, okay, I've been to the Euler tours. Gonna write this up now. But yeah, I don't know if you can see these huge black bags under my eyes. Okay, so I'm gonna stop the recording. Yeah, everything is in the lecture notes, or Karatsuba's algorithm is not in CLRS, I think, but Strassen's algorithm is. And it's also, it is in a different version. I just got this, I used the notation from Wikipedia. thank you for coming. And good luck with the assignment. Right, I have to post. We figured out when the TA's office hours are going to be this week. It's going to be like Thursday afternoon and Friday afternoon, but I have to remember exactly when, and post it on Brightspace. And there will be a tutorial on Friday, but it will be on this stuff and fast Fourier transforms. Okay, good luck with the assignment. Cheers. Stop recording. Stop.